relations and look at how we can find relationships among interval level variables. Last week we looked at contingency tables in order to understand relationships between categorical variables. Now we're looking at scatterplots and correlations so that we can understand interval level variables. Alright, so scatterplots show a relationship between two interval level variables. We'll see some deviations from what we see here underlined because we'll talk about dummy variables as well in this lecture. But generally speaking, for scatterplots, we're looking at two interval level variables. In a scatterplot, every case appears as a point on a graph. So, for example, we have two interval variables for 16 students. So the 16 students were asked the number of martinis they drank, and they were also measured their blood alcohol for their blood alcohol content. So in studying this relationship, we're trying to understand, or we're interested in understanding the relationship between these two numerical values to see how one is affected by changes in the other. So real quick before we move forward, which of these two variables do you think would be our independent and which do you think would be our dependent variable? So the number of martinis you drink, do you think it depends on your alcohol level, or do you think it's independent by itself and it may depend on something else like your upbringing or whatever, your gender, who knows? But it is independent is the independent variable in this particular relationship, and blood alcohol content is the dependent variable because it's dependent on how much you drink, how much you consume. So let's look at this table real quick, and we have the 16 students. Student 1 took in 5 martini drinks. Let's see, student 16 did about 4 drinks, had about 4 drinks. Student 5, we see here, this is not in any order, sorry guys, had 3 drinks and so on. And then we can see the blood alcohol content. I have no clue why I put this in this order. Nonetheless, we have student 1 with the blood alcohol level of 0.1, student 2 of 0.03, and so on and so on. Okay, so we're going to take and plot what we just saw in the previous slide, that table with each student and how much alcohol they consume, and then we see here as our independent variable, and we see our dependent variable is the blood alcohol content or level right up here. A scatterplot is a scatter of points, where each point denotes the value of an observation for two selected variables. Each point in this graph corresponds to the 16 students from the table in the previous slide. So we should be able to count all the dots here, and it should all equal 16. Okay, and so we had student 1, or we had the person with who drank 1 martini had a blood alcohol level of about 0.01, right? And the highest number of martinis drank by a student was 9 with a blood alcohol level of 0.19. Right, so we can see a trend here. We can see that the more alcohol you drink, if we were to put a line there, that line would probably be going from the bottom left to the top right. That would probably be the line, and that you can see would be a positive relationship. To look for overall pattern is the form. We'll talk about it, the direction, and the strength of the relationship. So the direction would be positive, negative, or no direction. No direction at all, okay? And we would be able to see that. We'll look at it in future slides. The strength of the relationship is determined by how closely the points fit on a straight line. Okay? The form is whether that line is linear, if it has some type of curve in it, or if there is no pattern at all and it's just a bunch of points with no clear pattern. And then we can have outliers, like we saw in the previous slide. There was the person who drank 9 drinks, and that person might possibly be an outlier in that particular case, possibly depending on some other factors. And these are strange deviations from the pattern. So whether it's in terms of the direction, it's doing something else, it's going in a different direction, or whether, it, but anywho, these outliers help us to understand strength, direction, and form. Okay, and it could actually cause that strength, particularly in the form, to deviate a bit. So we have, in terms of scatter plots, the direction. For a positive relationship, we see the direction going up, as we see in the left-handed scatter plot. For a negative relationship, it's going down, right? And we say up and down in terms of from left to right. So from left to right, it's going up. From left to right in the negative relationship, you can see that it's going down. So as x goes up, as x rises, so x is the horizontal line, so as x goes from 0 to 1 to 2 to 3 all the way to 10, as it's increasing, our y, which is going from the bottom to top, 0, 2, 4, 6, 8, 10 again, that is going up. So as we can see from the positive linear relationship plot, we can see that the first dot there at the very bottom is 1, and it's 1, 1. The second dot is at 2 for x, and it's at 2 for y. So it just went up. It went up in the x, and it also went up in the y. Now let's look at the negative relationship. That top part at the top left is looks like a 1 for x, but it looks like a 9 for y. So it went from x of 1 and then a y of 9. Then we go to the next one. The x is still going up because the next value is 2, so this went from 1 to 2. But what happened here? It's going down. It went from 9 and it's going down to 8. So we can see that as one is going up, the other is going down. Okay? Whereas in the previous one, the one on the left, was one is going up, the other one is also going up. Alright, so when there's no relationship, we cannot figure out what's happening, right? We just don't know, when there's no direction, because that's what we're talking about in this slide. When there's no direction, we can't say whether it's positive or negative. Because let's take a look at the top one, and it would be the same for the bottom as well. That leftmost dot there, if we go if that's a 1 for x, and then we go to the 2 position for x, we see as x goes up, y is going up. But then we go to the 3, right? And we can see when x is 3, there are 3 x's there, and they each have different points. So as x is going up, y is doing a whole lot of different things. Y goes up, y goes down, and then we move on to the 4 for x, and that one still has different things going on. And we can see the exact same thing at the bottom chart, scatter plot, where there's just we can't really see a direction. We just see a lot of dots. A lot of dots. Okay. Alright, some variables inherently have curvilinear relationships. For example, middle-aged people may engage more in politics or attend PTA meetings more than, say, 0 to 18-year-olds, and more than the elderly. So the middle age group would probably have a higher instance of occurrence of PTA attendance. That scatter plot would look like an upside down U, where which is essentially a curvilinear shape, where you would see sort of looks like the one designated here as curvilinear. It would be the opposite of that, actually, where young people would be at the left and right, and then older people, middle-aged people would be at the top of that upside down view. Okay. So the other graphs that you see here, whether it's a positive relationship or negative, that has nothing to do with form. That's simply direction. But we can see here that the form for those plots are linear, because if we draw that dotted line there, we can see the linear shape. Okay. So now we've talked about direction, we've talked about form, so let's talk about strength. Strong linear relationships will all seem to be fairly closely, fairly close to a straight line. Fairly close to a straight line. Weak linear relationships will be further apart. Their points will be further apart, and will tend to form a line, but it would be harder to really see that line. Okay. We can see here on the left a pretty strong relationship, because we can definitely draw a line through there. On the right, a pretty weak relationship, because we can still sort of draw a line there. I could see where that line might go. It would still go from bottom left to top right, but it's still sort of weak now. Alright, more about strength. Which of these do you think would be the strong or weak or moderate relationship? Well, in my opinion, right, I would say that the one on the right would be a pretty strong relationship. And the one on the left would be, it's still sort of strong, but it's a little bit more scattered than the other one. So I would say moderately strong relationship. When we have no relationship, we've seen both of these, I think, in previous slides. But when we have no relationship, knowing X tells us nothing at all about Y. So X and Y vary independently. They don't depend on one another. In other words, one variable does not really affect the other variable. So let's look at the no relationship on the left. We see that X can be 1 or 2 or 3 or 4, but guess what? Y is not changing. So X does not cause Y to change. Nope, doesn't cause it to change much at all. And this is actually an equation for for the line y equals 5. If you know any algebra, I'm not requiring that at all when you're in this class, but this is an equation for y equals 5, and x is really just not involved at all. And then the next plot, we see that x is still going up from, it looks like a little bit over 1, then we've got 2 and 3 and 4, but even though x is increasing, say for x2, at 2, x at 3, oh my gosh, yeah. This is the precise reason why there's no relationship, because x at 1 is at 5, x at 2 goes up to about 7, x at 3 goes down. So it's just this, if you were to draw this line, it would just almost be a horizontal line, very similar to the plot right next to it, which is completely horizontal. So x is not allowing y to just only go up or only go down. It's going up and down, up and down, up and down. There's no relationship there because positives and negatives kind of cancel itself out, and there's no relationship. It's null, nil, nothing. It's interesting that we have scatter plots, which are useful, especially for visual reasons, because pictures can. What is the saying? T- oh my gosh, something about 1,000 words. I can't remember right now. I've gone completely blank. Nonetheless, correlation coefficients is a way to sort of bypass or these scatter plots, or to be on one accord, right? Because the correlation is a single number summary of a scatter plot. Not just that, it never conveys as much information as the full scatter plot. It only summarizes the information in the scatter plot. Um, However, it is often more convenient to report a table of correlations for many variables than to report an unwieldy number of scatter plots. Trust me, I've had to do that. Intuitively, the relationship is strong if the points in the scatter plot cluster tightly around some straight line. Okay? If this straight line rises from left to right, the relationship is positive, and the correlation coefficient, we should also expect that to be positive. If that line, that trend line that we see, if it falls from left to right instead of rising from left to right, that relationship would be negative, which means that we should see a correlation coefficient that has a negative value, a negative sign beside it. And the reason why correlation coefficients are so important is because we can look at a graph. Three people can look at a scatter plot, and one person may say, "Oh, that's strong. That's definitely strong relationship," and another person may say, "I think it's a little weak or moderate, possibly." But with a correlation coefficient, we sort of different fields have their rubric for what they consider moderate, strong, weak, based on that particular number. So we're going to see that in the next slide. We, through the correlation coefficient, there are guiding principles. For one, the direction is very clear. You get a number. If the number has a negative sign to it, then it is what it is. It's a negative relationship. No guessing about it. The number is negative, so the relationship is also negative. Okay? You may or may not see a positive sign, but we know if we don't see a negative, then it's definitely positive, right? So, positive relationship is positive R. So when independent variables increase, the dependent variable also increases. You're going to see a lot of repetition here because, hey, practice makes perfect. So if you keep hearing it over and over, hopefully it'll really stick. Okay? So as one variable goes up, the other goes down. A negative relationship, obviously the R would also be negative. And so when one variable is going up, the other one is going down. So the guiding principles about strength is as follows. First off, correlation coefficients range from -1 to +1. That is it. You will not see a correlation coefficient that's 38. You will never see a correlation coefficient that's -1.3. That's not even possible. The only values are -1 to +1. So -0.38 is possible, +0.49 is possible. Those are all possible, right? Another thing to note that if the R, your correlation coefficient, if it's 0, there is no relationship. There's no relationship, okay? If R is -1 or +1, if it is 1 at all, then this is the strongest possible relationship there is. Strength is based on the absolute value. It could be -1 and it's still a very strong relationship. It just happens to be a negative relationship, right? It's +1, yeah, it's positive, but if we're talking about strength, we're only talking about its strength, not its direction. This might sound elementary, but trust me when I say people get this confused all the time. Okay, a negative sign doesn't mean that it's a weak relationship by no means. Okay, a positive sign does not mean it's a strong relationship. No, 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 no. You're confusing direction with strength. Okay, and so here's our rubric. Here's the very thing that I said in a scatter plot. You could say one thing and someone else could say, yeah, I don't agree. I think it's a strong relationship. But with correlation coefficient, not only can you kind of downsize your results output and not have to have, 8,000 scatter plots, you can have 8,000 correlation coefficients and it's just all listed there, right? It's easier to see. You can see those numbers and you can see from this rubric here that if a number is 0 to 0.29 for this class and possibly for social science, we're going to call that a weak relationship. Again, this might vary based on the field that you're in and the field that you're doing research in, right? So 0.3 to 0.57, that's a moderate relationship. 0.6 to 1, that's a strong relationship. Now we can add negatives to all of these numbers and that would still make it a weak, a moderate, and a strong, just as you see here. So for example, if it's negative 0.29, negative 0.29 is still 0.29, right? So we know that number is still a weak relationship. If it's negative 0.60, guess what? It's still a strong relationship. It's not positive. I was about to say that. It's negative 0.060. Negative 0.60. It's a negative relationship, sure, but it's a strong relationship. Okay? Direction is based on positive and negative signs. Strength is not based on positive and negative signs. Okay? And the one thing, as I said in the previous slide, that correlation coefficients cannot show you the way scatterplots show you is the form. Okay, so we don't know based on what that R is, if it's 0.29 and negative 0.29, we don't know if it curves, we don't know if it's a straight line, we don't know that. And so if that's something we really need to know, then we definitely need to look at a scatterplot. Okay? Matrix. Correlation matrix. We can see that all of the words in the first column, pay grade, salary, education, years of service, and age, we see them across the first row as well in the exact same order. This is a matrix, so that means it's sort of a mirror image, right? So the relationship between pay grade and pay grade should be a one-to-one relationship. There should be no change, right? That's like you comparing yourself to yourself. You are identical. And if one is the highest relationship strength, then of course across the board for any relationship with itself, it should always be one. Always be one. And so salary to salary, it's a one-to-one relationship. Education to education, and so on and so forth. It's all one-to-one. Okay? So next, let's take a look at salary to pay grade. Okay? As salary goes up, first of all, the number for the correlation coefficient is 0.911. Okay? And so if we go back to the previous slide, not only do we know that it's a positive relationship, without even going back to the previous slide, we know that this is really close to 1, so it's a pretty strong relationship. Okay? Let's take a look at some other examples. Education to pay grade. So let's take education. You can go across until you see pay grade at 0.606, or you can go to pay grade and go down, however you want to look at it. Either way, it's 0.606. Okay? And first, we know that it's a positive relationship, and everything on here is a positive relationship. We see no negatives, there are no negative relationships. So first, the direction is positive. Second, we know that the strength is also is strong. So it's not weak. It's not moderate. It's actually strong because strong started at 0.60 and goes all the way to 1. So the way that we interpret this, and please be sure to look at the notes under this to see sort of the way, the guide for how to interpret two interval level variables. Okay, these are interval level variables. Pay grade goes from 3 up to, I don't know, 16 or something. Salary goes from whatever goes all the way to, hundreds of thousands of dollars. Education can go up. However long you work at the federal government can go up. Age obviously can go up, right? In terms of from 16, 17, 18, and so on. These are interval level variables. And so the way we interpret it is the salary, the higher one's education, the higher their pay grade. For age and salary, we see that is 0.290. And so the higher the age, and we always start off that way, by the way, we always start off with the higher something, and then where you see capitalized, that is going to depend on whether this is a negative or positive relationship. So we say the higher education is, if that was a negative 606, we would say the lower the pay grade. If it was a negative 2.290, we would say the lower the salary. The higher the age, the lower the salary. So I'm gonna let you guys tell the story of these two questions here and provide the interpretations for age and federal years of service, and for grade and salary, which I think we already did actually. So get to it. So for interpreting dummy variables, this one is a little bit tricky, but trust me, not too tricky. Again, make sure you look at the notes for this PowerPoint to guide you on how to make these interpretations. If the ones that I provide here within the slide aren't as helpful, okay? So we have a correlation matrix here, and we see salary, which is interval, and we see two other variables, gender and race. In terms of male is the name of this variable, and black is the name of the other one, being dummy variables. And you've done this in your homework, but let me just reiterate that we use, for dummy variables, it is common to use the value that is the highest value. So if you have a dummy variable and the one value is 0 and the other one is 1 is what we call that variable. So we would never call this variable gender. We would never call that other variable race, because we need it to be more specific, because honestly we can do that since there are only two values. So rather than have to sift through the notes and go, I wonder how they coded this, gender variable, we just call it what it is, because there are only two values, male, female. And so male equals 1, so we're going to name that variable male. Okay? Black equals 1, so we're going to name that variable black, right? If this was not a dummy variable and it was white, black, Asian, Hispanic, then we'll kind of have to name that variable race. We have to, because we can't just say, this variable is called Hispanic because Hispanic is coded as 5. No. We can't do that. All right, so now let's get back to this correlation interpretation. So we have a dummy variable and an interval level variable. So say, for example, salary and gender. All right, this gender variable is named male, obviously because of how it's coded. If it was coded 0 for male and 1 for female, then it would be called female. So in this case, it's called male. So Again, look at your notes for how this interpretation is done. But essentially, what we're seeing here is that as the male variable goes up, salary goes up because this is this positive relationship. But we don't say that. That is just not the right way to say, to interpret that variable and that correlation coefficient. That's just not the right way to interpret that correlation coefficient. We would instead say males have higher salaries than females. So rather than saying as the gender variable or as the male variable increases, salary increases. Okay? Rather than say that, we just say what the increase is. So the increase goes from 0 to 1, so the increase goes from female to male. So males make more than females. If that was a negative value, we would simply say males make less than females. Okay? So let's try it for the black and salary. So as that black variable increases, the salary variable decreases. So we don't say that, right? We say as it increases, what is it increasing to? It's increasing to black. So as black, so it's saying that blacks make lower than that the comparison group, which is white. So blacks have lower salaries than whites in this sample. Okay. So then we have two dummy variables. Not the best way to best use of the correlation coefficient. It's typically not interpreted. But if we were to interpret it, this is what we would say. So we have the male variable and the black variable. So as black and Hispanic, as black and gender increase and male increase, so that means black males, there are fewer of them than there are white females. Kind of odd, right? Yes, but it's only telling us about the proportion in the sample that are black males. So black males are about 12% of the sample, maybe, but there are less of them than the others in this category. Okay, but again, a very weird use of correlation coefficients. We really use them for dummy variables with interval level variables or for interval level variables and together. Okay. Last week and this week we've talked about relationships. We've talked about them in terms of contingency tables, making something sort of that's complicated, trying to simplify it with contingency tables. And so now we did it again with scatterplots and correlations, trying to take something that's a little complicated and simplify it through a picture, scatterplot, or through a correlation matrix, correlation coefficients, a number, right? Finding relationships among variables is arguably the most important task in data analysis. You've heard this last week, you're hearing it again this week. So some things to remember: scatterplots are a graphical method for detecting relationships between two numerical values. Summary measures such as correlation coefficients can be applied to variables that are displayed numerically. Yes, they can. Actually, it simplifies it. And they are more appropriate for truly numerical values. However, they can be used for categorical variables that have been coded numerically, as we saw with the dummy variables. Okay, we can do that, particularly if it's dummy to interval. But if it's dummy to dummy, not ideal. Not ideal. But we can. Just don't. Not ideal. We're done with lecture 4. Feel free to review this lecture again or move forward and start practice exercise 4 and of course homework 4. Take care, guys.